Hello, everyone. Welcome to my talk. It's Hacking Exchange from the outside in. This talk covers some research a coworker and I have done. My coworker is Brandon Perry. He handled a bit of the Linux fuzzing, and I handled most of the Windows work. So, who am I? I am a senior research consultant with Atreides Partners. We are a boutique consulting firm. We do product security primarily, and we do anything from low-level hardware stuff to web applications. I have about 6 years industry experience. I enjoy Windows malware techniques and researching those primarily. Some Windows exploitation, powerlifting, and heavily edited photography, Mafia board game, and that's my Twitter and GitHub. It's going to be relevant later because there's going to be a CTF challenge for this. All right, the overview of the talk. So we're going to be covering fuzzing target selection, fuzzer selection, harness development, fuzzing optimization, the results, target selection for our fuzzing, target environment setup, and the reporting process. So, fuzzing target selection. When I first wanted to do this, I wanted to get a little bit more into fuzzing. So I talked to one of my colleagues, Brandon, and I asked for a target, and he recommended Oracle Outside In Technology. It's a it's an SDK that's meant to parse files primarily. It's developed using C++, so there's a lot of room for memory corruption vulnerabilities. A little more about Oracle Outside In. It's used for content extraction, normalization, scrubbing, conversion, and viewing. It supports over 600 file formats, so it's very complex. And these file formats include PDF, Excel, Word, HTML, and XML. The bolded ones are the ones that are going to be the focus of the research. So before we get into fuzzer selection, we need to understand a little bit more about the fuzzer types. There are a few. There's dumb fuzzers, grammar-based fuzzers, mutation-based fuzzers, coverage-guided fuzzers, protocol fuzzers, generation fuzzers, etc. There's so many. But we'll just cover a few right now. What are dumb fuzzers? There are fuzzers that really don't understand the target. They are programs that just throw random data at a target until it crashes. They don't understand it at all. The pros of using these kind of fuzzers are they're simple. You don't require any research. You just have a place where you can input, and you just throw random data at it. The cons, you don't really understand the target. The fuzzer doesn't understand the target. The fuzzer doesn't know what it's doing. It's really, really, really bad when analyzing complex file formats. So, yeah. Next, we're going to go over grammar-based fuzzers. The pros of using them, actually, before that, grammar-based fuzzers use something called fuzzing grammar to generate correct syntax for the fuzzing. So if we are fuzzing HTML, it really understands the HTML language. Now, the pros of using these, you get a deep understanding of the target, or the fuzzer has a deep understanding of the target, so it generates correct syntax. The cons is you really have to understand the target to build something like this. You can use a grammar-based fuzzer that's off the shelf, but for complex targets, these aren't going to be too useful because all the juicy bugs have been found because people are using these. And it's very labor-intensive, so you have to understand the target to build something like this and build correct grammar. Next, we're going to go over mutation-based fuzzers. These fuzzers take in some input called a corpus, and they mutate the corpus using techniques such as bit flipping. And the pros of these kind of fuzzers, they're very easy to set up and use, and you can generate a large number of test cases in a small amount of time and without a lot of resources. The cons of these are you're limited by the corpus provided. You can't hit all the code paths if you give a very limited corpus. And they're not really effective against complex file formats. Next, Coverage-guided fuzzers. Coverage-guided fuzzers use your corpus when, and sends it to the target, and it collects coverage information, so which code blocks were hit and which basic code blocks were hit. This gives the fuzzer the ability to understand the target a little bit more, and it allows the fuzzer to hit very specific edge cases. The way it studies the target execution is through a library called an instrumentation library. There are many that exist, but we'll be really using two, as we'll see later. So the pros of using a coverage-guided fuzzer, you get high code coverage. That's what the kind of fuzzer is used for. It's great for complex targets, but the cons are they could be resource intensive for the actual instrumentation happening. So if the target is very heavy and you have to instrument it, that can be very resource intensive. Also, the initial setup of the instrumentation library could be intensive as well. And we'll see how later it impacted our fuzzer selection. Next, we have protocol fuzzers. As the name suggests, these fuzzers are designed to fuzz network protocols. So pros of using protocol fuzzers, you test network protocols. This also leads to any bugs you find, there are going to be critical vulnerabilities. So if you think about a network protocol, it's exposed to untrusted users. So even if you have something like a null pointer dereference which causes a crash, you have a denial of service on this protocol. So you have to get it back up, and it requires some kind of maintenance. The cons of using this kind of fuzzer, it's complex configuration. It's resource intensive, so you are going to use a lot of system resources to actually track everything. And they're very target specific, so you can't really use an HTTP fuzzer to fuzz something like an RDP protocol. So now, for what we selected. We used American Fuzzy Lop, or AFL, with Dynast for Linux, and this was selected for familiarity. We also used Jackalope and TinyInst on Windows, and this was selected for ease of setup and use on Windows. If you recall earlier when I was talking about the instrumentation library, I initially opted into using WinAFL. However, it was very difficult to get the instrumentation set up. So both of these fuzzers can be seen as mutation and coverage-guided fuzzers. They collect coverage information, and they have a mutation engine that mutates the corpus to try to trigger some crashes. For the Linux setup, it was quite easy. Clone AFL, clone Dynast, compile applications. Additional Linux setup includes static instrumentation. That's the way we instrumented the libraries. We used a minimum block of 8 bytes because we observed that if you instrument anything less than that, it will cause some stability issues. For Windows, it's also similar. You install Visual Studio and CMake, clone the Jackalope repository, clone TinyInst and its dependencies. The second two bullets can be found on the Jackalope repository, all the instructions you need, and it just works out of the box. So the last one is compile and build. Now, as it stands right now, you have enough to actually get fuzzing done. You can fuzz the target and potentially find some crashes. However, you will be finding the only crashes you'll find are like the catastrophic ones, a null pointer dereference, a heap overflow that just destroyed the entire heap, etc. So this is where additional Windows setup comes in. Introducing gflags. So gflags is an application that's part of the Windows SDK. It can be used to enable a feature called full page heap. Full page heap does a few things. First, uninitialized memory. It fills it with a familiar pattern. It's a C0, C0, C0 pattern. So if the application references uninitialized memory and then tries to write to that uninitialized memory, let's say it picks up the memory from an allocation and thinks it's an address and just goes to try to write to it and it was uninitialized, that will cause a crash. Additionally, G flags, whenever there is an application, regardless of the size, will put one guard page on either side of the allocation. That's 0x1000 bytes. And what these guard pages do is whenever the application tries to read and write to those memory locations, it will trigger an exception and cause a crash. So the benefit here is we can detect overflows and underflows as soon as they happen. And we can also detect them regardless of how small the overflow or underflow is. Additionally, G flags, after an allocation is freed, it will mark the freed chunk as no access. So in a use after free scenario, after the object was freed from memory, when the program tries to reference that memory, it will cause an exception. So what are the pros and cons of using this? The pros are right there. You can detect bugs all day long. However, these allocations, especially the guard pages, they're going to be living in the memory the entire life cycle of the program execution. So for every allocation, regardless of how small, you're going to be using 2 pages of memory. Now, with the 64-bit address space, we have a little bit of wiggle room. However, this can be an issue later, as we will see when it comes to actual target selection. So some applications will have some thresholds that will cause issues for us. Now, we're going to move on to harness development. And before we go into harness development, what is a harness? A harness is a lightweight program that calls our target functions. It's responsible for environment setup, and it requires some understanding of the target functions and their input. Not too much, but just some. So as part of the Oracle Outside-In SDK, we have this nice application called Memory I/O. This was an example usage from Oracle for content access and data access. It takes in one argument, which is a file, specifically a file path that it will parse. And then its usage can be found below, Memory I/O, input file. Now, with everything we have so far, we could run the we can run the fuzzing campaign. But we want some optimization in our fuzzing. We want to get more executions per second. This is when we bring in some harness modifications and fuzzer modifications. Well, the fuzzer modifications weren't supposed to be there, but harness modifications. First, we stripped out all the debug statements from the Memory I/O file. And we also implemented something called shared memory. So instead of the fuzzer writing to disk, and then our harness reading the file, which is going to waste CPU clock cycles, we are going to be basically sharing the memory between the 2 processes. And this can be done with 2 functions calls, which we'll see later. Additionally, we wanted to implement something called persistent fuzzing, which will keep the application alive and just keep executing a target function. It will restore our register states. So that way, we don't have to waste clock cycles on destroying the application and restarting it every single time. To implement shared memory on Windows, it's very simple. You call these 2 functions, open file mapping A and map view of file. Open file mapping A just returns a handle, so it takes in 3 arguments, but it returns a handle to the shared memory. And map view of file will actually map the shared memory that you open the handle to into your process. So you can think about it as create file and read file, if you're familiar with Windows. This is our actual fuzzing command. So we have the inputs. There are a few flags to just look out for. The -T flag is for timeout. So how long does the fuzzer wait before it says that this execution timed out, so how long does it wait before our target function gets called? It's in milliseconds. I put it as 5,000. Next, the persistent or persist flag. That's for persistent fuzzing, which we talked about earlier. Loop will keep calling our function and restoring the register states. And iterations is how many times our corpus gets modified and how many times the target function is called before restarting the application. And finally, dictionary is a dictionary of strings or just things to help our mutating engine create some meaningful mutations on our target corpus to get some impactful results. Now, these are some helpful breakpoints that were very useful during debugging of our crashes. The first one is break on module load. This could be useful if you want to turn on debugging. Let's say there was a debugging system within our DLL or whatever. You use that as soon as the DLL loads, you can turn on debugging so you can get more information. When I say turn on debugging, it's usually going to check some flags that are part of the application, and you can modify those before actually executing any functions in the DLL. The next one is break on a specific hit. So if you think about you have a file that caused a crash, it might like the target function where the crash happened might be called 4 or 5 times. And our vulnerability only happened in the 5th execution, or the bug only happened in the 5th execution, or the crash. So we could use this to break on the 5th or whatever execution here. It was very useful for me when analyzing heap overflows. Next, logging allocations. So we will see that where this is specifically useful later. We made a breakpoint on NTDLL RTL allocate heap and at the return address of NTDLL. And in the first breakpoint, we store all of our arguments in pseudo registers that are provided from WinDebug. And then in the second one, we will print those pseudo registers. And in the case of RTL allocate heap, the first one is the heap handle, the second one is heap flags, and the last one is the size of the allocation. And what's being returned is the pointer. So this is going to be very useful later, as we'll see. Now, our fuzzing results, the meat and potatoes of this. We fuzzed 3 libraries. We had some unintentional results. We fuzzed VSXL5, VSPDF, and VSHTML. And they are responsible for parsing XL5, PDF, and HTML, respectively. The SCCUT.dll, this is a utility library that's part of outside in. It's more for setup and so on and so forth. So VSHTML, we found a single null pointer dereference, 2 stack overflows, and 1 use after free. With VSXL5, it's a lot more interesting. We found 3 heap overflows, 9 heap out-of-bound reads, a single out-of-bound stack issue. I believe it was an out-of-bound stack comparison, an integer overflow, which led to a heap out-of-bounds comparison, use after free, and divided by 0. Something that's interesting that we saw during this, when doing crash analysis of these, there are some interesting logic bugs where in a conditional statement, they will check the offset within a heap allocation and see if it's larger than the size of the allocation. However, in the else statement, they use that same offset, but don't check. And that caused an out of bounds. As we can also see here, actually, we'll talk about that later. VSPDF. This was really bad. We found 30 stack overflows, 8 null pointer dereferences, and 9 heap out-of-bound reads. And finally, the utility DLL, 1 use after free, 1 null pointer dereference, and 1 divided by 0. So here we're looking at everything. Now you can see this giant graph on the right. The others are much smaller. The giant stack, first let's look at the smaller graphs. Now, with the SCCUT function, DLL, this is a utility DLL. It's not doing any complex parsing. So not too much logic going on there. So all right, not too many bugs there. With VSHTML, I know for a fact from talking to other researchers that they have looked at this. So more eyes have been on this attack surface. Additionally, this could be also because we used a mutation and coverage guided fuzzer rather than a grammar-based fuzzer or a generation fuzzer. Now, VSXL5 and VSPDF. These are the worst two. VSXL5 we actually fuzzed for about 4 days. And we have all of these bugs. Also, with VSPDF, this was about 4 weeks, and that was because I was on a trip and I just left the fuzzer running. Now, the problem with these two is we noticed that there is almost almost no bounds checks, or none of the bound checks were correct, like with the conditional statement example. So there's a lot of these kind of bugs there that we can see. Additionally, it probably has had less eyes on this. So when you see later about potential targets, if anyone wants to do their own research, and if anyone is going to be attending the CTF, hint, look at these. Now, let's do a little case study. I use after free in VSHTML. Our fuzzer spit out that first file, or that first HTML, code. We manually trimmed the code down, and we minimized the test case, and we kept going lower or less and less and less until we got that one at the very bottom, the minimal crash, or the minimal test case for a crash. So how did we discover it to use after free? It's time for a demo. All right. I will explain what's happening here. So first, we run the debugger with our input. We have page heap enabled. Run, we have a crash. Okay, great. Now we want to find out how many times was this code address hit. So we first get the offset within VSHTML, set up a breakpoint there. So you'll see that. And then we set up our counter to see how many times that breakpoint, that breakpoint got hit before the crash. So we're going to go eventually. Okay. And now we should be seeing the counter. It's 2, so it hit twice. We're now going to turn off page heap so we can see exactly what's happening. We can see the size of this memory chunk, etc. So we clear the breakpoints, clear everything, turn off page heap. We're going to restart the application, and then we're going to set a breakpoint for the second time that code gets hit. So that's a breakpoint from earlier. We see our register and the vulnerable, block. And we can see that it's free. So this bug is a use after free. Now, back to our slides. Now, if you recall earlier when I said we were logging the allocations, what we ended up doing is we know the size of the heap chunk, that caused the use after free, or that was responsible for the use after free. We logged all allocations and all frees during program execution. Additionally, we printed out all the stack traces from when that's happening. So through that, we ended up identifying both the constructor and destructor of the vulnerable object. We identified that this object is specifically a tree node object. And over here, we can see the logic and where the initial bug is that caused the crash. So when the destructor for this node is getting called, it's first going to check if the node has any children. If it does, it's going to decrease the child count from the parent. Then, if this node that's getting freed is the leftmost child, it's going to remove that and make the right sibling the leftmost child. And it's also going to remove the reference from the freed node to the parent. However, it's not checking if it's the rightmost child. That is the bug, or at least that is the initial logic. It's doing the sibling removal correctly. Now, if you guys are noticing, it didn't check if this node had any children. So there was another bug here, but our crash happened as soon as this next logic was hit. So I just realized actually, let's go back. Looking at these tags, specifically, so it's building the binary tree with the 3 tags we have here. It first creates the root, and then it creates left sibling, right sibling, and then adds a child to the right sibling. And then when it sees this frameset tag, I looked up the frameset HTML tag. Apparently, it's an HTML file that doesn't have any real tags. It's just a bunch of iframes. So what's probably happening is it's trying to free it, expecting that this is going to be a frameset HTML file. So as soon as it gets the frameset tag, it frees it, and then it tries to create a new node, probably for the frameset. Now, let's look at the patch. We can see that logic was added for the rightmost child now. Additionally, there was, if we go back to the actual use after free, so it was deleting the node, and then it was trying to create a new node that would under the parent, and then when it's adding the right sibling is the use after free. So it's right now deleting everything properly, and it removed that call for creating a new node. Additionally, we can see a new function was added to free any children. So that's a good job on Oracle's part there. Now, for target selection, we ended up looking up VS-HTML on Google, and we can see the patch from 2012 for Microsoft. There is a patch for SharePoint as well. So we saw the patch for Exchange specifically, but there is a patch for SharePoint. I don't know if SharePoint still uses this technology. We also see that Oracle SQL Server and Oracle Web Center Content Server uses it. So if you want to do your own research, potentially look at that. Now, for target environment setup, how to set up Exchange, you have 2 Windows servers that you need, one acting as a domain controller and one acting as Exchange server or running Exchange server. You will need the Windows SDK on the Exchange server for G-flags, and use static IP addresses. If you use DHCP, as soon as the IP addresses, especially of the domain controller changes, you're going to have a bad time and Exchange will just stop working. Also remember to snapshot your instances. I think I'm an Exchange admin now because I had to rebuild the environment about 5 or 6 times. So yeah, I learned the hard way. Now, Fast Information Processing Filter Service, FIPFS. This is a component in Exchange that's meant for data loss prevention, malware scanning, and spam detection. It has a component called scanning process, or a program called scanning process, which is the component that we're going to target, which utilizes Oracle Outside In. On the right, we can see a picture from Process Explorer, where we hovered over the scanning process, and we enumerated the DLLs, and we can see all the outside-in DLLs are there. So now, when we saw this, we were trying to send emails, and nothing was happening. No crashes, nothing at all. Turns out you needed to do some configurations. So specifically, I think it's because of the spam detection and DLP stuff. So you need to add new Exchange mail flow rules, which you can do that with the ECP panel. And you go under mail flow, and you do a new attachment inspection rule. Over here, we're just looking for the string AAAA, and it's for any email going to the administrator. Now, if you recall earlier about the downsides of using page heap, this is it. When we set everything up, and then we turned on page heap, and we were sending in our test cases, this scanning process was running out of memory. It's reaching its memory threshold before even processing our file. So after some digging, there is that configuration.xml file. You need to modify it to increase the memory max and process memory capacity as well. With our testing, these values seem to work just fine. Keep in mind, you're doing all of your crash analysis on the Oracle Outside-In libraries, so you don't need Exchange to do that. So, yep, modify this configuration. Lastly, turn on page heap on scanning process. This can be done with just this one function. Now, triggering the crash, at any point in time, there's going to be 3 instances of scanning process running, and there's a watchdog on top of that. In order to identify which scanning process is going to be the one that's processing the file at any given moment, you can just send an empty email to the target, and you should see that one of the scanning processes loaded vs.html.dll. This is because emails can have HTML embedded. So after you see that, attach your debugger and send your malicious attachment and wait for the crash. And pray to God it is going to crash. Now, finally, for the reporting timelines, in December, we submitted this to MSRC. In December 20th, Microsoft acknowledged that they received our bugs. And then on the 20th again, we got another response from Microsoft. Our trigger for VS.HTML wasn't working, so we sent 3 more triggers. And then MSRC acknowledged our bugs. Then Oracle released the patch, and we were telling Microsoft, like, hey, hurry up, we need to disclose this. Or like, we had a blog written for this and everything. So Microsoft asked to see the blog, and the blog was very detailed on how to do this fuzzing. And very shortly after, Microsoft announced they're decommissioning this product entirely, and they should be building their own soon. So there was a little back and forth between Microsoft, because in the advisory, there was no credit. There was also no bounty. I mean, they marked these bugs as critical initially. So finally, after talking to the right people, we got acknowledgement in April, and we got our bounty. So acknowledgement, Special thank you to Nick Nam from Atreides, Brandon Perry from Atreides, and Jordan Whitehead. So Nick Nam was responsible for handling a lot of the communications with Microsoft and MSRC. Brandon selected the target and did a good amount of the Linux fuzzing. And Jordan helped quite a bit with the crash analysis, specifically that use after free. Also, special thanks to Lisa Olson from MSRC, who actually helped us get credit and our bounty. And I guess closing remarks, I wanted to make sure this talk is simple, that anybody could do it. This stuff isn't that hard. It's just a lot of people make it seem a lot scarier than it is. And in order to get everybody to do that, if you paid attention to those slides, there's going to be a challenge in the CTF tomorrow. If you do it and you get any crash, come see me and I will give you a challenge coin. So, all right. Thank you, everyone. Thank you. We have a lot of time. What's up?
Yeah, I have a question about the fuzzing setup.
Yeah, what's up?
So when you're doing the page heap guards, it seems like you'd be leaving a ton of memory with every allocation. If you're doing persistent fuzzing, it would seem like you're resetting the program. Are you resetting the page heaps there, or are those page heaps continuing to be?
No, so the page heap is like, okay, so what he was asking is with persistent fuzzing, if I understood you correctly, are you going to be resetting the page heap every single time? Well, with about 5,000 executions, you're going to have plenty of room in 64-bit address space. So it's not going to be a problem, and after 5,000 executions, you're going to restart the application anyway with a fresh memory layout. It's going to be, everything is empty, so it's not a problem at all. Yeah. What's up?
When you had that issue with the mail rule, that you had to actually create one of those in order to get the exploit to fire, or like to bring up the loading of the DLL?
Yes.
How did you encounter that was the solution to make the DLL like load? What was the process?
Persistence, to be very honest with you. And the configuration too with the memory threshold is like, you just go keep reading documentation and some stuff is just not documented well enough for you to understand what's going on. So you just keep adding and changing different configurations until something clicks. Yeah. Anyone else?
I got a question for you, man.
What's up?
Considering that both coverage-guided fuzzers and ground-based fuzzers are difficult to set up and they require a little bit of tuning in order to get them up and running,
Yeah.
what are the pros and cons in choosing one over the other for a different, target?
Well, for our specific experience, or from this fuzzing campaign, it was quite simple to use a coverage and mutation-based fuzzer because I was fuzzing different file formats. So you don't need to pay too much attention to grammar. The grammar is very, very, very specific to the target. Whereas the VSHTML bugs, I guarantee you'll find a lot more bugs if you use a grammar-based fuzzer there. So that's...
Hey, when you showed the Google page,
Yes.
I couldn't tell if you already knew that Exchange used outside in when you started researching it, or if you learned later after realizing you could get it to crash.
I learned after getting a few crashes. So after specifically fuzzing VSHTML, I learned that outside in was vulnerable. That's why the lookup had VSHTML. And I just wanted to show to Microsoft how bad this thing is. So I fuzzed the other formats just as a, complement. Right. Anyone else?
Where did you get the corpus to feed the mutation?
Very good question. Okay, so for the PDF and HTML, I used, I forgot, it's on the blog, but I used a repository called Fuzzing Corpus. And it just has like a bunch of different file formats and a bunch of just different files. However, with the Excel, I use Google Dorks for the file format, and I just downloaded a bunch from the internet, and yeah, that did it.
For the machine that you were running fuzzing on, was it a especially well resourced? It was running on the laptop?
Yeah, very, very good question. It was running on this. It was running on this, and sometimes it was running on a much less powered Intel NUC. So once again, this is how bad this target is, and you guys should look at it. Anything else? Thank you, everyone.